老师，你知道又是谁吗？
老师，一个不接。
好了，
少佑阿贝。
好，先听这里为。好，那我们上一次上课应该讲到化石，应该很讲。
6、7页。
对，我们讲了。
阿公6、7。
对，我们讲了很多化石。好，听这里。好，那化石这个东西呢，原则上呢，我们就只能根据挖到的东西做出一些判断，做出一些判断。好，那怎么判断呢？通常都取决于科学家的经验。有这个点就是科学家怎么样去解读这个化石带来的一些东西。好，那这个东西呢，我没有办法真的告诉你科学家是怎么判断的。估计你以后也不会去挖化石。
不会啊，我有挖到过。
我说你不会挖化石起来研究。
我有挖
去挖那个坟墓就好了。
坟墓不是化石，这是死人骨头。那不是化石。
他摆了几年，不是肉都
去挖什么的坟墓？
那是骨头，那不是化石，化石是石头。
现在的坟墓不是化石，但是以前。
化石这个东西基本上死掉以后要埋起来，经过一些物理化学作用，它要变质，变成石头。那我们那些骨头，坟墓的那些骨头，基本上才放下去没多久。要形成化石，大概要几百几千年以上才有机会。你能埋下去几年呢？挖起来是骨头，挖起来是骨头，它需要一段时间，没有那么快。
老师有没有可能其
不是
实暴龙？
会有什么肾脏那些，啊，什么都会不见。
这个有。
换你讲话了哦。
烂掉。
换你讲话了吗？
好的。
好，我在这。
好，这文哲要问什么？
有没有可能其实暴龙它的脚只有这样，然后结果它的脚其实它的脚其实现在是它的，
它是什么？
就是它现在的脚是它的手，就是现在拼出来的脚它。
理论上应该没有，因为它暴龙也是爬虫类嘛，所以它理论上应该还是有前肢跟后肢，只是它的前肢就比较
它是小鸟长出来的。
萎缩一点。好，要我
看其他的一点长文型的一点。
你要说一点都没有，当然是有一点，但有一点没有什么意义啊。应该是讲暴龙，现在有跟暴龙类似的东西啊。
蜥蜴。
应该是讲恐龙，恐龙虽然死光了，但是有跟恐龙差不多的东西留下。
科摩多巨蜥。
现在跟恐龙关系比较近的，你们每天都会看到。
壁虎鸡。
就是鸟，就是鸟。鸟就是一种长得比较奇怪的恐龙。然后严格上来说，鸟就是一种长得比较怪的恐龙，大概是这样。好，那听着你。好，那今天是放心玩科学，但我没有办法真的拿化石给你玩。
老师，我问你哦，如果我把一颗蛋，就是那种没有受精的蛋，弄到只剩气势，然后那个蛋黄跟蛋白剩超少，我可以拿来做实验吗？只是应该还要一阵子。
我没有听懂什么意思。
就是它不是越不新鲜，它的气势就会越大。
对啊。
那如果我把它用到气势很大，然后我可以拿来这里做实验吗？就放心玩科学的时候。
超臭。
它早就已经坏掉了。
好吧。
好，那因为我没有办法真的拿化石给你看，好，所以我们看一些。
我们现在去挖化石。出发。
我们看一些科学家挖到的一些化石。
然后我们去非洲啊。
让你呢知道一下这个科学家怎么样对这个化石做解读 ，OK？
因为我这白色认真到我在投篮。
骨头就是骨头，
加拿大。
不要用白色，对黑的
加拿大。
好，所以我们稍微看一下
黑人的骨头
化石。我稍微看一下这化石。
我问你哦，
知道一下。
那黑人我是不是更不会看到？
各位，我们现在看影片。
Planet Earth was a land of giants. Snakes the length of buses.
I am still to this day.
这么屌，
然后那个是什么？那个
我的大屌。
Completely self-mounting.
Ocean killers with jaws big enough to swallow a person whole.
These jaws were able to rip out this big chunk of carb.
And predators that dwarf T-Rex.
We're talking something of an enormous length that could slice you with one motion.
好玩吗？
Of all the creatures that have ever lived,
这谁的？
which is the biggest? Using the latest discoveries and cutting-edge science,
哎，看
我讲过。
你波折和这个，
到这种病，
高层轮到你讲话了吗？问你了吗？
对啊，
管东管西，你家住海边是不是？
你也是一样，
你也住海边的。
我没有管东管西啊。
we're going to reveal a top 10 of the biggest beasts ever that have walked the earth, swum the seas, and soared the skies.
这种太屌了。
你他妈怎么不说霸王龙是一午餐？
那霸王做努力啊。
依旧是
Analyzing
霸王
the
龙。
ultimate giant beasts across the animal kingdom,
Wow, that's
species by species, and using length as our ultimate guide.
哎，你们如果不要看，我们就上课。
哦哟，这一下在吵什么？
真的。
We count down from 10. And first on our list is a creature you never expect. A terrifying beast. The biggest insect that ever lived. Long before the dinosaurs, a winged giant terrorized the skies. Flying at over 20 miles per hour, and with jaws that can cut small reptiles to pieces, its common name is the griffin fly.
然后开始公大师了。
哦，
A clue to this ancient megabug was discovered in
然后为什么以前的
1900
生
in
物
Little
大
County, Oklahoma.
哎，应该不能讲以前比较大只，是他都拿大只的给你看，
所以它其实有小只的。
有小只的，只是
奥兰。
小只的比较没有嘛，没有这种，因为它是电视节目啊，它需要吸引人啊。
那为什么以前有大只的，现在没有大只？
哎，有一
In
些
the
原因
southern
啊，
United States.
他会讲一些原因。
Today, it's the job of insect expert Brian Farrell to take care of that clue.
哎，
fragile
你
fossil
是用拍到的。
that's 275 million years old.
It's really a spectacular fossil.
This fossil is the largest insect wing ever discovered.
To get an idea of just how big this insect was, this is a reasonably large size modern dragonfly. For comparison, it's about 1/5 the size at most of this Meganeropsis.
Looking at this single wing, it's clear just how big the griffin fly could get.
这可以让我做起。
啊，他现在没有活着。
It had 4 wings.
有的话你早就看到了。
以后你应该不会玩这个市场。
它飞进来。
它已经绝种了，
飞机
这已经灭绝了。
他不都是？
他现在讲的都是灭绝的吗？
哎，有还活着的。
你说那个蛇吗？
好，那如果对，如果你会被挡到，
可以前面。
你可以左右移一下，可以左右移一下。这我是在上。你可以自己稍微移一下，你左右移一下。好，那我这里要讲这个东西，好，那因为这个是国外的影片，好，所以 国外呢用的单位呢习惯上跟我不一样，这里用的单位叫做英尺。
你住海边啊？管东管西。
我住山边。
这里用的单位叫英尺，好，英尺呢大概是30公分。好，所以他这里说的2尺半大概就是75公分。好，所以其实它的翅膀有75公分。
哇，很长哎。
75公分。
好，那因为我们昨天上次
你说一边翅膀75公分？
没有，是2边加起来。
差不多我脖子的程度了。
无所谓的味道。
高层在喷什么？
录下，我来录下。
高层的正。
不要再喷了好不好？
很臭哎，
很臭的啊！为什么要在秘密空间喷这个？
这有水准啊？
没有水准。
极微大开哇，好臭！开这个旁边。
好，回这里。好，那我们上一次有讲化石的，好，所以想一下。
跟教练讲，上课分析。
不要提我书包啊，不能够。
如果你要弄别人，就会去做。好，那我们上一次有讲化石，好，为什么蜻蜓留下来的化石做翅膀？
咖啡。
喷体被当作肥料。
因为很明显它没有骨头，所以基本上呢很难挖到它的化石，所以留下来那个是类似于痕迹一样东西。
Be across. That makes it 6 times larger than many modern dragonflies.
6倍。
If it was around today, it would be a match for a hawk and span the outstretched arm of a 6-foot man. From smaller and more complete fossils, experts have discovered that dragonflies didn't really look like dragonflies. Their anatomy was incredibly similar.
所以，
把它拉起来，把它拉起来。
快点拉起来。
我不要啊！求我啊！
你去多去的是。
好，那你来讲，应该中间就可以了吧？中间，这样应该可以吧？
哦，你什么东西啊？
大
嘿，你兄弟在
大蜻蜓，
大蜻蜓，
然后大蜻蜓，
大蜻蜓，
有75公分
在哪里啊？
哎，
蜻蜓，
身高很多。
好的，
我给他画，我给你见，我。
它已经落地了。
是我拿给你多了。
好啊，那回来这里。
不用。
开灯啊！
又来。
电源。
对，还那个有。
好，
我看你赶快别了。
这样可以吧？各位。
不要拖了，不要一直扫。5分钟没关系的，等下走过。
啊，你们到底好了没？
好了好，你在喷什么啦？犯错。
好啦。
So it's likely that they behave in the same way too, as deadly hunters. Anthony Leonardo is a world expert in dragonfly flight. He's unlocking the secrets of what makes these flying aces such expert killer beasts. They have 4 wings that can beat independently.
If you look at the wings closely, you can see that they're quite amazing. The dragonfly can fly forwards, backwards, upside down. It can also pull these incredibly sharp 6G turns.
They also have eyes with virtually 360-degree vision,
注意，
powerful wings for grabbing insect prey, and killer jaws.
They have massive mandibles, so these kind of teaching creatures, and they very quickly cut and slice all this prey up into little bits and be able to swallow it.
But how did the griffinfly get so big? And why are modern dragonflies so much smaller?
什么啦？
The answer lies in the way all other insects breathe.
Insects don't have lungs. On the outside of the dragonfly's body are little openings called spiracles.
These are little holes that open and close, and they basically are little pumps letting air into the dragonfly's body and then pushing it back out. Once through the spiracles, the air moves through a network of tubes called trachea. This way, oxygen is fed directly to every single cell of the body. The problem is, there are so many tubes, there's little room left for muscle. And that's what stops today's dragonflies getting any larger. So how did they ever reach the monstrous size of the griffin fly? How did they pack enough muscle into their bodies to power giant wings? One paleobiologist at Midwestern University, John Vandenbrooks, believes he has the answer. He's doing experiments to uncover the secrets to what makes a bigger bug. John thinks that growing bigger was all down to the amount of oxygen in the air they breathe.
Oxygen was much higher in the past. Today, oxygen is about 21% of the atmosphere around you. In the past, it was as high as 31%.
An extra 10% might not sound like much, but that's 50% more oxygen than we breathe today.
So perhaps that increase in oxygen in the atmosphere is what led to the possibility that those insects get as large as they did.
To investigate,
如果你不想看到蟑螂的，你可以暂时不要看黑板。
John decided to do something radical.
超大只蟑螂。其实我
Change
们应该没
the
在怕。
oxygen that bugs could breathe.
好像有。
First, he takes cockroaches and breeds them at far lower levels of oxygen than today.
In this top chamber, we have cockroaches reared under lower oxygen levels, about 12%. And you can see how large this individual is.
It looks large, but it's actually small for the species. John then rears other roaches at the oxygen levels of the
把它
bugs.
吃掉。
我靠！
Comparatively, the cockroaches reared down here are being reared at a high oxygen level of about 31%. And you can see now how large this individual is. Much larger than those reared at the lower
太
oxygen
大
levels.
了，
And it's even
这
more
可惜
impressive
吧？
if we're able to compare the two animals.
The results are clear and astonishing.
在我呢？
Oxygen bugs can have a store into their breathing system.
啊，那么效果。
We can now definitively say as oxygen goes up, it actually allows for the animal
这大宝宝有没有那么大只啊？
so it can have
宝宝在环境开的。
really large, vicious predators that we see 300 million years ago.
Had we been around to witness it, the griffin fly would have been a truly terrifying sight.
这只是基本。
This was the biggest insect ever to fly Earth's skies. But our next beast is far, far bigger. Fast forward from griffin fly to 27 million years ago.
现在不是有人是两只吗？哎，我的鸡啊！
Feathered giant.
这已经灭绝了。
With wings as wide as a 2-lane highway and a cruise speed faster than Usain Bolt, it could travel to every corner of the planet.
我们还有吗？现在没了。
已经绝种了。
真的进阶区。
The evidence of this giant first came to light in South Carolina in the USA. In 2010, paleontologist Dan Sepka discovered a collection of bones in a storeroom at the Charleston Museum.
When we pulled open the drawer and saw this for the first time, it was just absolutely spectacular.
Laying the bones out, Dan could see this was no ordinary find.
It has this skull with these bony, toothed jaw that almost looks like a crocodile.
But it wasn't any kind of reptile. What Dan had discovered was the largest flying bird of all time. a new species they called Pelagornis sandersi.
This massive element here is the humerus. This is the first bone of the wing skeleton, so it's equivalent to the upper arm bone in a human skeleton. This bone in particular is longer than my entire arm, so we have a remarkably long wing.
The giant bird's body was 6 feet long. With a 24 feet wingspan, the largest bird alive today, the wandering albatross, could fit easily under one of its wings. Pelagornis' wingspan rivaled that of a Harrier jump jet. Everything about the skeleton tells us this bird must have flown. But how could something this big possibly have stayed airborne? A closer look at the bones provides Dan with a vital clue. Like flying birds today, its bones are hollow and super thin.
The bone wall is about 1 millimeter thick, and so this animal would have been very lightweight for its size. There's less weight to support in flight.
It rivaled the wingspan of a fighter jet, but this giant bird weighed only
一磅大概是0.45公斤，
那么轻，
所以48磅大概是21、22公斤左右。
48 pounds.
大家可以看我做起，
Less than a third of the weight of an adult human.
你会把它踩爆。
不会，
Light as it was, one bone still cast doubt on its ability to fly.
This bone, the scapula, is the equivalent to our own shoulder blade. And you can see it's just so small. It's actually almost comically small, and this certainly reveals that this bird was not a high-powered flapper.
If it wasn't flapping its wings, how did Pelagornis fly? Flight biomechanics expert Mike Habib believes the answer lies with this.
I'm out here to try hang gliding for the first time. Really excited. I'm hoping this will give me some idea of what being a Pelagornis will be like.
A hang glider has a similar wingspan to Pelagornis. It's also lightweight, has a hollow tubular skeleton, and a large rigid wing.
The physics don't change, so an airplane wing or hang glider wing looks fundamentally very similar to an animal wing, even though they're made of different stuff.
The only way Mike or Pelagornis could get airborne would be to run into the wind.
Hoping that I run properly and launch, and I don't have to be like one of these people that gets dragged along on their face. You ready to take off? Let's take off. Okay. This is awesome. Oh man. This will give you a little bit of a glimpse of what it'd be like to be a giant flying animal in the past. This is an amazing feat of engineering, and it's a great way of soaring. But Pelagornis did a lot better.
27 million years ago, nature produced a glider that was about 4 times more efficient than this hang glider. In fact, Pelagornis was a better glider than anything that has ever lived, or that technology has ever produced.
So we were there for 10 minutes, very long flight, but Pelagornis would have been one of the champions of long-distance flight. Probably could stay in the air for weeks at a time, maybe even months at a time.
Staying aloft for long periods was essential for Pelagornis. Its bony teeth, ideal for catching fish, reveal it was a seabird.
27 million years ago, Pelagornis was living in this open sea environment. Pelagornis could probably travel across thousands of miles of ocean without much thought.
So how did Pelagornis manage such an extraordinary feat? Dan thinks the clue may lie with the modern master of ocean flight, the wandering albatross. Albatrosses make use of the way air flowing over the oceans can change speed. They perform perform a daredevil maneuver called dynamic soaring. Dan believes if Pelagornis was to survive out at sea, it must have done the same thing.
So if we look at the waves, the wind above the waves is going more slowly than the wind higher up at a higher altitude above the waves, especially out on the open seas. And dynamic soaring birds can use this to their advantage.
They swoop down to the ocean surface, then pull up at the last second. Pulling up gives a bird enough momentum to rise up and catch faster moving air currents. Flying in loops like this, Pelagornis would have been able to cover vast distances and grab fish from the surface whilst burning very little energy. This was the biggest and most efficient flying bird in the history of the planet. It ruled the ocean skies. Pelagornis was at the limit of how big birds could grow and still get into the air. But if you think that's big, coming up at number 8 is an absolute whopper. Imagine walking into a modern zoo where they somehow managed to resurrect the largest mammal to walk the earth. What you see is this. 20 tons of hide-bound flesh, standing more than 2 stories tall. Evidence of this ancient mega-mammal emerged in the 20th century in what is now Pakistan. But today, this evidence is far from Asia. Paleontologist Mikhail Fortelius is investigating an extraordinary collection of the beast's bones in London's Natural History Museum.
Easy.
This colossal skull is testimony to its sheer size.
The head sits on a very long neck. There's never been anything similar to this.
Put all the bones together, and you get something that looks like a cross between a giraffe and an elephant. It's called Paraceratherium. It was so big, a 6-feet man could easily fit between its legs. It stood 25 feet high. It was nearly twice as tall and 3 times as heavy as the biggest land mammal today, the African elephant. And at 26 feet from nose to tail, it was as long as an Abrams battle tank. Now the obvious question has to be, why did it get so big? But there's an added complication. While some scientists believe that Paraceratherium lived in thick forests, Mikhail Fortelius thinks this creature's habitat was harsh. Afflicted by dry seasons when water was scarce and vegetation sparse. How does an animal become a giant when food is in short supply? Mikhail Fortelius believes the answer lies in the teeth.
Looking at the teeth will allow us to understand why this animal got so very large. The teeth are worn in a way that only happens when you're eating leaves.
And for eating leaves, sheer height would give this animal a massive advantage. Like a giraffe, it could get to food that's beyond the reach of most animals. So that explains Paraceratherium's height, but not its massive bulk. Fortelius believes that the explanation for that can be found in the harsh environment itself, that the animal grew big because of, not in spite of, its tough surroundings.
If you're small, just one day without water is a terrible thing and may kill you. But the larger you are, the more buffered you are, the more you can deal with harshness in this sense. You can go without food, without water. I think that's what was driving the size increase.
Not everyone agrees with Portelius' theory, but there's no doubt that somehow Paraceratherium thrived. And it must have consumed vast quantities of vegetation every day. To find enough food, it needed to range over hundreds of square miles. And that may be the reason for what is perhaps the most remarkable thing about this amazing animal. Its feet. Biomechanics expert John Hutchinson has analyzed Paraceratherium's foot bones and produced a 3D model. He's struck by just how much it resembles that of one of today's giants, the rhinoceros. In fact, weighing in at only 1/6 of its size, the rhino is Paraceratherium's closest living relative. And Hutchinson's research shows that in terms of size to weight, its feet must bear the heaviest loads.
Rhinoceros, the pressures of its feet are way higher than in a horse, a human, even an elephant. Rhinos already today are living at an extreme in terms of foot pressure, and Paraceratherium seems to have pushed that extreme further.
On the feet of both the rhino and its ancient cousin, there are 3 gigantic hoof-like nails. There's also a fatty pad designed to act as a shock absorber. The Paraceratherium's foot is proportionally more slender than a rhino's, meaning it has to bear even more stress.
My calculations suggest that Paraceratherium might have borne as much as 50% more pressure on its feet than a rhinoceros does.
In fact, this was the heaviest mammal ever to walk the earth. And John's calculations suggest one extraordinary fact.
Paraceratherium would have put more pressure on its feet than an average tank's treads would put on the ground. That's pretty staggering.
This was the biggest land mammal ever. And with footsteps this heavy, you'd have been well advised to stay out of its path. So far on Top 10 Biggest Beasts Ever, we've met a deadly dragonfly the size of a hawk, a giant bird the size of a plane, and a mega mammal twice the size of an African elephant. But next up is an even bigger beast that could launch into the skies. This is the closest Earth has ever got to a real-life winged dragon. 70 million years ago, while the dinosaurs ruled the Earth, the skies were ruled by pterosaurs. Their name means winged lizards. And paleontologist Gareth Dyke has spent more than 10 years of his life hunting them.
Pterosaurs are interesting because they're the first group of vertebrates to evolve powered flight, long before birds and long before bats.
The hunters brought him to Romania, to the region of Transylvania, better known as the home of that legendary monster, Dracula.
Years ago, the climate in this area was much different. Big islands in a tropical sea with lush vegetation, lots of animal and plant life, and quite high temperatures. Couldn't be more different to the weather today.
These red sandstone cliffs hold a huge number of fossils. As the rock erodes, more and more are revealed.
So what we have here are some of the bones of pterosaurs that we've collected from this area in the last few years. This one, for example, it's about 6 centimeters in length. So it would have come from an animal that would have had a wingspan of 1 or 2 meters, 6 feet. Average size for pterosaurs.
But then, in 2008, colleagues climbed down the cliffs and discovered something extraordinary.
This neck vertebra from the same part of the neck in a giant pterosaur. It's quite short, quite robust, but gigantic compared to a normal-sized pterosaur vertebra that you can see here. And you can see immediately that we're looking at animals of gigantic proportions.
When the neck bone was mapped onto a model of the pterosaur skeleton, it became clear that this was one of the largest members of the pterosaur family ever discovered, comparable to giant specimens found in the USA. At up to 16 feet tall, these massive pterosaurs could stand nearly 3 times taller than a human, tall enough to look a giraffe in the eye. Their front limbs were also vast wings that, when unfurled, could stretch up to 36 feet across, the same as a modern Learjet. It had a beak more than 5 feet long, perfectly suited to preying off other animals. And no living creature has ever had a larger wingspan. While it seems obvious that giant pterosaurs flew, they're so large, experts have puzzled over how they ever got off the ground. We already know that Pelagornis, with its 24 feet wingspan, was as big as a bird could get and still fly. The difficulty of just getting off the ground at this size stopped flying birds getting any bigger. So how did a 550-pound pterosaur with a 36 feet wingspan get into the air? Flight biomechanics expert Mike Habib has made it his mission to find out. He has been studying the bones of one particular giant pterosaur, Quetzalcoatlus. Discovered in Texas, this species is of similar giant size to the one found in Transylvania. Mike focused his attention on the pterosaur's wing.
This is the skeleton of Quetzalcoatlus. You see the massive bones of the wing. This is called the humerus, the bone of the upper arm.
Mike conducted a forensic analysis of the bones.
I used CT scans to look inside the bones. I found that most of the bones in the wing were very hollow. The bone wall is only 3 millimeters thick. It's mostly air by volume.
This makes the skeleton very light, but inside the upper arm bone, a dense internal scaffold reinforces the bone, especially near the shoulder. And that's not something you see in a bird wing. This bone is far stronger than needed for flight, stronger even than needed for walking. So why would the pterosaur possibly need such powerful forelimbs? Then Mike noticed another clue. A giant groove in the bone. This could mean only one thing: a huge tendon.
A giant tendon would run in along the groove here and wrap around the wing pivot joint and end up at the tip of the wing. The tendon would have been about as big around as my wrist.
The super size of this tendon led Mike to form a unique theory. The pterosaurs were using the tendon's elastic power to catapult themselves into the air.
Tendons, the muscles attached to them, have sort of springiness. You can stretch them, and then they snap back. Basically, a giant crossbow.
Mike used the skeleton to model how this might work.
A giant pterosaur like this one, to take off, would start by crouching on its back legs. Then it would unload the legs first, vaulting over the giant wing. Then it would push against the ground, using up all that stored energy and pushing itself as fast as possible into the air.
There is still one living creature that uses this kind of vaulting launch. It's plain to see when you watch a vampire bat take off. But vampire bats only weigh 2 ounces. So could the same principle work on the scale of a giant pterosaur? has come to a local firing range to find out.
So what we have here is a modern crossbow, and it's a very effective way of talking about pterosaurs. Giant pterosaurs would be stretching its tendons by crouching. The crouch phase would be much slower than the launch phase. So it puts the energy in slowly and then lets it out quick. So I'm going to put in the energy here